A very good morning to all the participants and speaker for today's session. We welcome you for the day 4 of the FTP. So I'm happy and privileged to introduce the speaker of today's session, Mr. Sridhar Artham. He's currently working as Senior Staff Engineer, Audio Group in Audience Communications India Private Limited, a knowledge company with a total 15 years of experience in the field of speech and audio coding and processing, speech enhancement and voice recognition on various embedded platforms, porting, optimization, integration, and customer interactions. He is also an expertise on various DSP architectures like ARM architectures, RVDS, DS5 open source, GCC tool chains for ARM, 10 Silica Hi-Fi platforms, and QDSP. He has hands-on experience in porting, optimization of audio speech codecs, and processing algorithms on ARM, 10 Silica and QDSP platforms, floating to fixed point conversions. He is also an expertise in customer interactions and cross-functional teams, in mentoring, guiding the team, and he has an exposure to system-level architecture for embedded development. He has excellent programming skills in C assembly languages on various embedded platforms and MATLAB, Perl, and Python. So we hope the participants will have a nice interaction time with sir. Over to you, sir.
Thank you very much, ma'am, for the introduction. So without wasting my time and the team's time here, so let us start the session. Do you people see my screen? Madam, are you guys able to see my screen?
Yes, it's visible. It's visible.
Yeah, thank you. Yeah, thanks for the introduction, madam, once again. And yeah.
So could you please turn on your video as well?
Sure, ma'am. Yeah. Yeah, thanks once again for the MS Ramaiah Institute of Technologies, EC department, for conducting this session. And yeah, this is one of the very prominent topics in vehicle communications, because this is a field where a lot of growth is there and a lot of development is going on. And I'm very much privileged to give a talk on related to the speech and audio signal processing in the in-vehicular communications. So these will be my agenda points for today's discussion. So I'll be discussing a brief on the various signal processing techniques which are present in the in-vehicle communications, emphasizing more on audio and speech signal processing. If you want to achieve those audio and speech signal processing techniques, you should require a specialized hardware. That is what we call it as a digital signal processor. So I'll be discussing in detail on the digital signal processors. Based on their kind of architectures, we can categorize them as a floating point and a fixed point. So I'll be taking you over through these floating point and the differences between floating point and fixed point architectures. Since floating point architecture is a little complex to understand, I'll be starting with the fixed point in detail, and I'll be going very deep dive into the fixed point implementations. So I'll be taking over through the various operations which are present as part of the fixed point implementations of these signal processing techniques on the digital signal processors. So after going through these kind of various signal processing techniques and their implementation on the fixed point DSP processors, I'll be taking one of the very prominent processor, that is ARM processor, and I'll be taking a kind of a complete life journey of this ARM architecture and how that is evolved and how we are using in various applications. And at last, I'll be giving a detailed explanation how we will be implementing any algorithm, any signal processing algorithm on the DSP. That means like it is more on the industry oriented, like how we do in our day-to-day lives in the industry. So these will be my agenda points for today's discussion. Now, if you see, there are various DSP functionalities or DSP functions which we encounter in the in-vehicle communication or in day-to-day life. So let us confine our discussion more onto the in-vehicular communications. Now, if you see, the more prominent things are filtering, which is one of the DSP functionalities where we will be making a sound field control. This sound field control is nothing but where we will be reducing the sound, or what you say, more prominent, insulating the sound based on the our DSP using the DSP functions or the signal processing functions without changing much of the hardware, like, and then volume control, and then AM FM demodulations, like whatever we hear the songs, it is like what we get is AM or FM related stuff. Means like they are modulated with that modulation techniques. So you require DSP signal processing function that is nothing but a modulation or demodulation in order to play those AM or FM signals. Now coming to the image processing. So image processing is one more the DSP functionality where we will be capturing the images, or we'll be sending the images, we will be decoding some images between the vehicle communications, and even while parking. These all things require the image processing. So for example, if you want to transmit a picture, so you cannot transmit the raw picture as it is, whatever you have taken. The reason is like it contains a huge amount of data, and it requires huge amount of bandwidth to transmit over the channel. So you require a best signal processor or best hardware in order to reduce the data which is present in that image to transmit, or which will be helpful in the transmission. That is what is the image processing. And for example, when you are taking any pictures based on this camera, so if you notice that when you are taking a picture in the mobile, when your hand shakes, what will happen is like you will get a flickering image. So if you want to remove those flickering images, you require a advanced hardware for that one. So that is what nothing but we will be doing with a specialized hardware of the removing of those noise present in that image. Coming to the speech processing, which is very, very important, or which is more prominent in most of the in-vehicle communications. Like speech processing involves noise suppression. So when you are talking on the phone while you are sitting in the car, so what will happen is like there will be a lot of engine noise will be there, a lot of surround noise will be there, and a lot of people will be sitting and talking. So when the person is talking, when the particular person is speaking, so these all surrounding noise and the surrounding effects which are present in the car needs to be removed. So it requires some speech processing algorithms like noise suppression algorithms, echo cancellations, and then, for example, if you want to issue a command to the, for example, if you want to issue any commands like playing some music, or starting the engine, or what you say, cleaning the, means like starting the wiper, starting the lights without touching physically. So giving a command. So those commands are nothing but a speech. It is nothing but a speech or speaker recognition. So this is what means like these are some of the what we can consider as a functionalities which are involved with the speech processing. And then if you want to transmit some data, so for example, if you cannot transmit the raw speech data as it is. As I mentioned, like the image, even voice also consumes huge amount of data. So if you want to reduce the size of that speech, you need to do encode. So that is nothing but you can consider the band compression techniques or various other compression techniques. It is one more functionality of the signal processing algorithm. So if you want to transmit the data, you require some kind of a equalization. Channel equalization needs to be done. Otherwise, it can introduce a lot of artifacts. So that is nothing but a equalization. And then if you want to, model the speech signal, you require a linear prediction. And then, for example, if there is one more functionality called error correction. For example, if you are getting some speech data from the other party, so for some reasons the data has been corrupted or is been not able to be received. So what will happen is like you will see a glitches in the speech. So you need to have some error correction mechanism for such kind of things. So these are the various high-level signal processing techniques which we can consider as part of the in-vehicle communications. So these processing algorithms, they are very highly CPU intensive. For example, let us take one speaker recognition. It's a command, voice commands. So if you want to model that one, first of all, your speech needs to be modeled upfront, and it should have the model file. And then later, when you are issuing the commands, your processor or your hardware should be capable enough to generate those features and to compare those features with the existing model, whether the person is uttering this word or some different word. So it requires it is very highly computationally intensive functionality. So normal hardwares, normal generic processors will not be able to handle such kind of functionalities. And if you see the noise canceller, so noise canceller can be done using a regular typical mechanisms like in the time domain or frequency domain, or you can use the neural networks in order to model the noise to suppress that noise. And even for the echo cancellation, you can model the complete core infrastructure in such a core infrastructure, and you can remove the echoes which are coming from that car. So this requires very highly computationally intensive. And for example, it has to do some parallel processing. It cannot, all this may not be serial processing. It can be parallel processing as well. So if you want to handle such kind of functionalities, you require a specialized hardware. Now, if you see a kind of a detailed thing in the, let us confine our discussion more onto the car here, so that it will be very easy to understand for us. Now, if you see some of the functionalities where the specialized hardware is required. Now, if you see here, engine diagnosis. So there will be some kind of a sensors where the sensors will be collecting the data which is present. Maybe like we can consider whether the brake is working properly or not, whether the fuel transmission is proper or not. So those kind of data, sensor data, will be taken, captured, and will be given to the hardware. That hardware, what it does is basically it processes the data and it defines whether the engine is working properly or not. So this implies more like whether the engine is safe or secure, safety for the safety driving. This is very much required. Now coming to this navigation, I think most of the people are aware that this navigation is nothing but the maps. So where the data will be coming from the cloud and you will be decoding here locally and it will be displaying here. So this requires some specialized hardware, it's a parallel processing, what I mean to say. So along with this kind of a diagnosis, this will be going on. For example, if you get a call, speech call or something like you are playing some music and all that one, so you require some audio processing here. So this will be in majorly if you see here, sound, digital audio, sound field control and sound image control. For example, if you come to the very advanced car infotainment techniques, so where this sound image control, what it does is basically it creates an environment in such a way that you are in a particular place. For example, you want to attend a meeting, so you are traveling in the car, so it has to create a kind of an image or create a kind of an environment where you are present in a kind of a conference room kind of thing. So such kind of things can be done using this sound image control. These are the advanced car infotainment techniques, I say. But the basic techniques like echo cancellation, howl cancellation, basically right, if you see here, when you are on the speaker phone and when the mic and the speaker are nearby or the volume levels are very high, what will happen is you can see the echo and howling effect will also come into picture. So you have to remove those echo cans, because echo, when the other person hears the same of his voice when he is talking, it will be very annoying. So you require to remove that echo. And then, as I mentioned, right, when the mic and the speaker, they are nearby, so that howling effect will come into picture. So that howling effect needs to be cancelled. And as we discussed in our previous slide on the various other signal processing techniques like this speech recognition and speech synthesis, this is one of the very, very important or more prominent nowadays, I say. So if you want to do all these kind of signal processing technique, these are the various techniques in general. So if you want to achieve this one, you require a specialized hardware, because all these can be in parallel most of the times. So handling of these things with a normal processor may not be possible. The reason is that because they are very highly CPU intensive functionalities. Now we will see how the DSP is special in handling these techniques, and what are the specialty in the DSPs. We will little deep dive into that one. So far it is clear, right? Any questions?
Yes, sir, it's clear, sir. You can proceed, sir.
Yeah, thank you. Now, let us enter into that specialized hardware what I was talking about. So basically that specialized hardware, what we call it here as a digital signal processor. The reason why we are calling as a digital signal processor is basically like we are implementing the digital signal processing algorithms on this hardware. So the name has come as a digital signal processor. So where it is processing the digital signal data. So you can do whatever kind of a computations you want in the digital format in that processor. So you'll get the analog data converted into digital data. The digital data will be given to the processor, and the processor will do the digital processing and use of the digital data. Once again, it will be converted into the analog data or whatever format, and this is the generic functionalities of the digital signal processor. This is a basic data flow. So I'll be discussing in detail about it in the coming slides. Now coming to this, what is this digital signal processor? It is a specialized architecture for implementation of the signal processing algorithms. So why not the generic processor like Intel? We have the latest versions of the Intel like i7, i9, all those things. Why can't we use here? They cannot handle these high computational signal processing algorithms. It will take huge amount of time to do this kind of a processing. So because they don't have the special architecture. So what is the special architecture? We'll be going in detail. So basically, one of the advantage of the digital signal processor over the general processor is it is very low power consuming. So you cannot assume that the processor can consume whatever data, whatever amount of power it is there. For example, you will be playing some songs, you will be talking when the engine is off. So at the time it will be battery operated. So if it is power hungry, what will happen is like the battery will get drained very soon. So one of the important characteristics of the digital signal processor is it is very low power compared to the general processor. The reason is it has a specialized architecture. So most of the things will be done by that hardware itself. So no need to have the more power consumption over there. And compared to the general processor, the digital signal processor is very compact, very, very minute. If you see your mobile phone where it has a digital signal processor, it's very, very minute one. So if you take your computers or these things, right, it is a general processor where it occupies huge amount of space and it will consume more amount of power. And compared to this general processor, right, it is very much cost effective. If you see the digital signal processors, what we sell from the audience, it is like hardly $0.5 or $1 or maximum of $2 based on the different architecture of the functionalities. But if you take the general purpose processor, you will not get for any $2 or $3. You have to spend at least $50 or $100 kind of thing. So this is cost effective. And then one more special feature of the digital signal processor is it is programmable. Programmable in the sense like you can change the functionality. For example, you might have dumped the image to do some noise suppression. Later point of time, you need to upgrade in the sense like it has to some more enhancements to the existing functionalities. You don't need to change the processor itself. You can just reprogram and then update the software. Then automatically those new features will be effective. That is what we say programmable. So you can do multiple number of programming to that one in order to change the or to enhance the existing algorithm. So without it does not require any hardware change. Sometimes it requires, but most of the times these enhancements can be done without changing the hardware. So you can reprogram how many number of times you want. So these are some of the basic functional, basic differences between the general purpose processor and the digital signal processor. That is why we choose the digital signal processor to implement the signal processing algorithms. So when it comes to the what are the means like how can we differentiate the various digital signal processors? So it can be differentiated based on its operations. For example, you can have a fixed point processor and a fixed floating point processor. So what do you mean by floating point processor is basically when the data is in the floating point format or in the fractional formats, you can use the floating point processor. It is very easy to implement, but when it comes to the hardware architecture, it has to handle this fractional part. So it requires some extra specialized hardware compared to the integer formats. So floating point and fixed point, depending on the operations, what you are using. So DSP can be a floating point or a fixed point. So usually floating point processors will be more cost compared to the fixed point and more power hungry compared to the fixed point. When it comes to the implementation rate, directly you can write the floating point code and you can run it on the floating point processor. But as I mentioned, right, it is little more cost compared to the fixed point and power hungry. So people will be preferring more to on the fixed point compared to the floating point. And depending on the instructions, what are the various instructions? Like what we say, most of us might have studied our microprocessors or microcontrollers, where we will be having the various instruction set where the directly processor will be understanding. So depending on the type of instruction set, like a reduced instruction set, very small number of instructions, you will be able to handle the most of the operations. That is what the reduced instruction set architecture. Now coming to the complex instruction, means like you will have the multiple instructions which can be executed in parallel. That is what the CISC architecture. So these are the couple of things which we consider for differentiating between the different digital signal processor internally. Now coming to the applications. So if you ask me, I don't see a place where we are not using the digital signal processor. We are using the digital signal processor almost everywhere nowadays because it's advanced. If you take the washing machine, if you take the refrigerator, if you take the what is the smart watches, you take the mobile phones, cars, car infotainment, wherever you go, this digital signal processor is a mandatory item which is present as part of this one. So this is a brief about the digital signal processor. Now we will go little deeper into the signal processor related stuff. Now if you see here, these are the what I was mentioning about the applications here. Now if you see here, this consumer audio and then car infotainment, where you see the means like it is used in most of the places in day-to-day life. Now we will see how the data flows or how the DSP is operated, how the data is obtained to the processor, and then how it is going to process and how it is going to give. Here, this is a typical thing for the speech and audio signal processing. Even it can be equally applicable for the other sensor related items like diagnosis of the engine transmission, engine control, those things that is coming, the data will be coming from the sensors, and the data, usually the sensor data, most of the times it will be digital, or even if it is in the analog form, it will be converted from the analog to digital converter and will be given to the digital signal processor. So you can consider these are the inputs, this is the digital signal processor, and this is the output. So inputs can be from the mic, or input can be from the cloud internet, or inputs can be from the sensor. So the data before entering into the signal processor, that will be converted into the digital format and will be given to this one, will be given to the digital signal processor. So this digital signal processor, what it does is basically it takes the digital data based on the operation, it will try to do that functionality and give the corresponding output. Let us take the noise cancellation. So the data is captured from the mics, and that data is converted into the digital format using the analog to digital converter, and the data is given to the digital signal processor. So that mic can contain both noise and speech. So the digital signal processor, that based on this noise cancellation algorithm, what it does is that it separates the noise and speech, and it filters out the noise part, and it will give the speech part to this one. So what this will happen here, and a digital to analog conversion will happen, and the transmission will take place. This is one of the example what I'm telling here. Now let us consider the speaker recognition or speech recognition. So the same thing here, the mic data will be captured here. The data is converted into the digital format. If it is having the noise cancel, if it is having the noise, A noise canceller will be applied here, and then noise-free data will be coming out. And the data, whatever you got here, features can be extracted from the speech frame, and that will be compared with the existing model. For example, hey Alexa, play some music. So hey Alexa is a keyword which it will invoke the processor. Okay, so it has to recognize that hey Alexa. So how it is recognizing? It models that hey Alexa frame, and it constantly keep on checking whether the person is uttering this keyword or not. So that processing will happen here, and it will send an event. For example, a keyword is detected. What it will do next time? What is the command is using? Okay, after doing the keyword detection, the speech command it will take. It will take directly the speech command. Sometimes it will be done in the locally, that is without using internet. The processing will be done here itself. That is called the edge computing. If the data is transferred, to the cloud, then the processing is happening in the cloud. That is called the cloud computing. So accordingly, it can be done here, or it will be transmitted to the cloud. So like this is the generic typical data flow in the DSPs. So we will see how this data is collected, which are the interfaces will be used here, how the data is transferred to the digital signal processor. We will go little in detail in the upcoming slides. Now I'll be discussing a little more in deeper on the DSP architectures, like as we were discussing on the floating point and fixed point DSPs, right? So I'll be going a little deeper into that one, what this floating point architecture means for us, what is the fixed point architecture means for us. So what are the various DSP algorithms, and what is the motivation to be have a specialized architecture for the signal processors. And there are some kind of in the architectures, you'll have some parallelism and pipelining. So these are some common terminologies what we see when we choose a digital signal processor. So I'll be going little in detail. What is this parallelism? What is this pipelining? How that is going to affect the throughput of your algorithm? So those things I'll be discussing in detail. And then there will be a memory management unit. So you should have some kind of a unit where it controls the memory accesses, memory reads, memory writes, all those things. So I'll be discussing in detail about these topics in the upcoming slides, like IO interfaces, as I mentioned here, right? So if you want to collect the data and if you want to feed to the processor, you should have some IO interfaces. So I'll be discussing a little deeper into this IO. What are those IO interfaces? And then, as I was mentioning about the instruction sets, right? Like a reduced instruction set and a complex instruction set. So I'll be discussing a little in brief. I will not be going a little deeper over there. So I'll be discussing in brief about the differences between this one and where they will be useful. Those things I'll be explaining. So if you want to evaluate a DSP, so I'll be discussing these things in the upcoming slides. Now coming to the how you evaluate a DSP. So for example, if you want to implement a DSP algorithm, so DSP1 is taking this much amount of memory, DSP2 is taking this much amount of memory. So memory is one of the very important aspect. So maybe like we might have seen here the 16 GB RAM, 8 GB RAM, but when it comes to the DSP, right, you have to make sure that your memory should be very minimal. The reason is memory is very costly. So the memory which is used in the DSP is very, very fast. Instead, it is a single cycle read, single cycle write. So if you want to achieve that one, you should have a very limited memory. So if you want to evaluate your algorithm, the memory footprint of that algorithm should be minimal. Now coming to the how many cycles it is taking, how many operations it is taking. So if it is taking more operations, it is more power hungry. It consumes more cycles. So it is more power hungry. So you have to reduce the memory, you have to reduce the cycles for the corresponding algorithm. Yeah, there will be a trade-off. It means like both cannot go hand in hand. Sometimes if you want to reduce the cycles, memory will be increased. If you want to reduce the memory, some cycles will be increased. So depending on the use case, we will choose that what needs to be done over there. So let us enter into a little deeper understanding in this DSP architectures. Now let us go into a little detail on the floating point. Means like I'll be giving a brief introduction here. I'll not be going so deep here as it is a little complex to understand from the hardware perspective. Now coming to the floating point arithmetic. So usually the data size will be 32 bits or 64 bits. So if you consider, I think here most of the people might have some hands-on to the C or C++ programming. because there is a now mandatory subjects in the engineering side. So now if you see here, most of the people might be aware what is this float and double data types, which is present as part of the C or C++. So float is a 32-bit variable where it can contains integer part and fractional part. Similarly, double, it is also a integer and the fractional part will be there, but the size of that one will be the 64-bit. So if you divide those 32 bits, how you are going to represent in the digital domain? Because if if you, for example, if you want to store a variable in the float format, like the value is 32.565, let us consider. So how it is going to be represented in the digital format? So basically there is a standard called IEEE 754 format where these 32 bits are divided like this. So one bit is allocated for the signed, means like whether it is a signed or unsigned value, positive or negative value. And coming to the mantissa, means like the integer portion, it will have the 2 to the power of 8, those many number of values you can represent in the for the mantissa part. It's like it is very big dynamic range will be there for that one compared to the fixed point. We'll see the what is that fixed point. Based on that one, then we can judge what is this dynamic range and all that one. Okay. And then when it comes to the fractional part, it is allocated the 23 bits. So these 32 bits are divided into this format or this fashion based on the IEEE 754 format. So if you see here mantissa bits, it is 8 bits. Means like 2 to the power of 8. Those many number of values you can represent. Means like basically 2 to the power of 120. It's a very high dynamic range. And because of 23 bits you are allocating for the fractional part, it will have the very great resolution. Means like you can represent very small values with a better accuracy. That's what it means, the resolution. Now, if you want to do this floating point arithmetic, you should do customization in the floating point unit. Like in any processor, you will have a separate unit called floating point unit, where it handles the floating point operations separately. So as I mentioned, right, this is a specialized hardware. So it requires some separate unit itself. So some DSP processors, it will come with an optional floating point. So if you want to use the floating point, you can use it. If you don't want, you can just remove it. So if you include that floating point unit, what will happen is like it will be like more power consuming and it is more cost compared to the integer processor. So if you're removing the floating point unit, what will happen? It is a basic integer format. So integer digital signal processor or the fixed point digital signal processor will cost less and it is less power hungry compared to the floating point unit. So some processors like in the ARM, if you take the latest cores like the Cortex ARM v7A architecture, Cortex A8, A9, A73, they comes with the optional floating point unit. So if the algorithm means like if the use case is demanding that I can implement everything in the fixed point, I don't want the floating point unit, so remove it. So what will happen is like cost of the processor will come down, power consumption will come down, and most of your hardware will become much more simpler. So this is some basic understanding on the floating point arithmetic processor side. Now let us go little in detail on the fixed point side. How does that look like? Now if you see here, as I mentioned in the name itself, like fixed point arithmetic means like the number of bits are very much fixed here and it is not going to change. For example, if you are telling the 32-bit architecture, the data types will be remaining in the 32-bit. Means like all your registers are based on the 32-bit of size. So it does not have any floating point in the sense like decimal and fractional part that will not be present when you do the fixed point arithmetic. Those things will be represented in the integer format. For example, I have a value of 0.33. So you can represent in the fixed point based on the quantization formats, what we call as a Q formats. So if you see here, is a basically, right, if you see the data types in the floating point, we were using float and double. But when it comes to the fixed point arithmetic, as I mentioned that it will have the only integer type of data types like short format, which is of 16 bits, integer formats, which is of 32 bits, long, which we consider as a 64-bit. So when you consider, right, like you'll have the different quantization formats. So depending on the values which your algorithm is able to process, okay, we will be choosing that kind of a format. For example, if my values are ranging in between -1 to 0.9999, these values. So you don't have any integer portion here. It is maximum value is up to 0.999. So you can have just one signed bit and the rest of the things you can allocate for the fractional part. Now let us consider if your value is more than this one, like 1.98 or 99, that is the maximum value you are getting. So you can choose one extra bit, means like that is 2.14 format, means like you are removing one of the fractional part and you are allocating to that integer part, because you can lose some of the fractional part, but if you lose the integer part, your total value will become different. So you'll be allocating more bits for the integer portion, reducing the number of bits which are used for the fractional portion. So that way you can interchange here, but the overall length of the bits will remain unchanged. It will be 16, means it is 16 bit fixed. If it is 32 bit, it is fixed 32 bits. That's it. So you will be shuffling here and there. Okay, it is depending on your algorithm. So usually what we represent is in the qm.n format, like 1.15, 2.14, 3.12, like that. So basically we'll be changing here. So if you take this one, right, you can have the range based on this format. This will be your range of values, what it can occupy. So if you take 1.15 format, what will happen? So if you apply this formula, it ranges from minus 32,768 to 32,767. But if you transform into the fractional part, right, it will be like minus 1 to 0.99. So how do you convert from here to here? Just divide by the maximum value, which can be represented with the 16 bits. Nothing but minus 32,768 divided by 2 to the power of 15. Nothing but same thing, same value you'll get. That is minus 1. Here 32,767 divided by 32,768. So you will get a little lesser than 1. So this will be the maximum value. So the beauty of this one is if you multiply to Q1.15 format. So like if you take 0.5 into 0.5, it will be within that range itself. It is not going to into the it is not going to overflow. So that is one of the beauty of that one. So this is what is a fixed point arithmetic representations will be there. So how many levels it can represent depending on the number of bits you choose. For example, if you choose 16 bits, these many number of levels, means like those many number of values you can accommodate into that bit format. So if you want more resolution, you can increase the bit numbers, total number of bits. So you can choose the 32-bit processor or you can choose the 16-bit processor depending on the use case. For example, I am operating on the speech. So speech may not require more than 16 bits. So you can confine to Q1.15 format. But when it comes to the audio, like music processing or music playback kind of thing, right? Usually those things will occupy the 32 bits because it requires more resolution. It contains not only voice, it also contains the musical instruments data as well. So that musical instrument data will not be that clear or that great in the 16-bit format because it will have the reduced number of levels. So you can choose based on the use case. If you choose 16 bits, you will have a certain kind of a range of values. And if you choose 32-bit, it will have more values compared to the 16-bit data type registers. So now compared to the floating point, it will have the very low dynamic range. You see here, you will be able to represent in between only these values. So it will have the low dynamic range compared to the floating point. Floating point means it's very huge. You can represent 2 to the power of 128. That much amount of values you can represent in the floating point format. But this is compared to the floating point format, this is more cost effective, more means like more power efficient. So that's where we need to choose depending on the use case. We will be tended to use whether we have to use the fixed point or a floating point. So general arithmetic operations, like whatever you take any DSP algorithm, any signal processing algorithm, what it involves? It involves mainly additions, multiplications, multiply accumulates, roundings, saturations. Only these kind of operations will be involved if you take any signal processing algorithm. Okay, if you take any FIR filter or IR filter, whatever kind of filtering mechanism you take, finally it boils down to addition, multiplication, multiply, and accumulate. Only these things will be present. Whatever you do at the end of the algorithm, only these operations will be there. So we will look in detail how this fixed point arithmetic. For example, when we see these ranges and these numbers, right, we will see a little confused how these additions are done and how these values are reflected for this fractional part, because nowhere else you see this fractional portions while you are doing on the fixed point. You will see only these numbers, but how they are corresponding to this one, we will see it. We will see the operations. We will go a little deep dive into the fixed point arithmetic operations. So, but what are the challenges in the fixed point coding is, so directly you cannot write this one like floating point code, the way like how you are writing the floating point code, you cannot write the fixed point code. So it requires some specialized training, specialized techniques, because if you see here, you are representing -1 with the 32768. So if you want to code in such a way using this integer format, it requires some extra effort. That is what one of the major challenge in the fixed point coding. So we'll see how the C codes looks like and those things in the upcoming slides. So far, any doubts or anything which I need to cover more? Okay. If
No,
not,
sir, you can continue. It's interesting, sir.
yeah, thank you. Now, if you compare between the floating versus fixed, as I was keep on telling, okay, fixed is low power and less complex compared to the floating point. But what is the advantage of floating point? It is very easy to implement. Easy to implement, like you can write the normal C code in the floating point operations, okay, which is very fast. You can, it's like you can bring up your algorithm to the processor very fastly, but it is more power hungry, and you will have the more dynamic range in the floating point compared to the fixed point. So basically, right, in the implementation of algorithms, you have to choose, okay, as an engineer, we have to choose whether my fixed point is required, floating point is required, depending on the operations. For example, if you want to do a speech coding, okay, where it requires only 16-bit, as I was mentioning, right, if it is a speech coding, you don't require huge number of bits. Of course, nowadays, super wideband algorithms, those things has come into picture, wideband related stuff, where the number of bits used are little more and even the sampling rates are more. So you may get a better clarity, but it's okay. Means like you don't recognize as a normal human being or a normal layman, right? You may be not able to differentiate between those things. So you can use for speech coding related stuff, you can still use the normal 16-bit DSPs. But if you want to go for the image processing kind of thing, where it requires a huge dynamic range, you cannot accommodate in the fixed point. So what you will be doing? You usually you'll be tending to go to the floating point. Yeah, it is more power hungry and more costly. That is fine, because I have to implement my image processing algorithm, which is not possible on the fixed point DSPs. So these are some of the use cases, what I need to say. So if you take speech recognition or speaker recognition, okay, you can choose a 16-bit input and you can have a 30. Okay, why you want to have a 32-bit registers, right? For example, if you multiply 16-bit by 16-bit, what will happen? You will get a 32 bits. So you require intermediate registers of 32-bit of size. So if you choose a 32-bit architecture, a fixed point, you can be still able to visualize or realize the speaker recognition or noise suppression or speech coding kind of things. But when it comes to the image processing or video processing kind of thing, right, you may require a more resolution, more dynamic range. You can go for the floating point kind of a process. And when it comes to the complexity of the architecture, right, floating point is too much of complex compared to the fixed point, because in the floating point you need to handle more number of bits, more amount of dynamic range. So the way it is representing is little different. It's like it is not integer format. You have to extract the magnitude part, means that is integer portion. You have to extract the fractional portion, and you have to convert it into that kind of a format, IEEE 754 format, what I was telling previously. So you need to convert and then you need to do the operations over there. So as a layman, when you are writing, right, as an engineer, you may not see that kind of a hard while writing to the floating point code. But when it comes to the architecture wise, right, it is more complex. But when it comes to the fixed point, for a layman or an engineer, if you want to code in the fixed point, it requires some extra skills. But when it comes to the architecture hardware side, it is simple. So these are the basic what we can consider as the differences between the various different architectures in these things. Let us move little into the further related and the fixed point related operations. So as I was mentioning in the previous slide, right? So most of our signal processing will boils down to addition, multiplication, and then subtraction. And then multiply and accumulate kind of thing will be there. Okay, if you take any of the signal processing algorithm, if you ask me any signal processing algorithm, that boils down to only those kind of operations. Okay, though that seems to be little funny, but that is the fact. Now let us see, we'll take one small example, how the addition is done in the fixed point. Okay, let us take for a simplicity of our discussion, 8-bit format, a character. If you take in the C language, right, a character, short, and integer. Character will have the 8 bits, short will have the 16 bits, and integer will have the 32 bits. Let us take a char where my register length is only 8 bits are present. Now, how I will be, if you reduce the number of bits, what will happen? Your resolution will be reduced. Okay, your resolution will be more reduced compared to the 16 bit because you are using only 8 bits for your representation of the numbers. So this is for our simplicity I'm explaining, but usually, right, if you take any speech or audio, we don't use the 8 bits. We will be minimum, we will start using the 16 bits. So let us take some example in the 8-bit character side, and where I'm representing 1 bit for the sign and remaining 7 bit for my fractional portion. Means like my values are ranging from -1 to 0.999 itself, but the actual values are -128 to +127. If you see here, right, this is the range what we will be saying. Now, if you see here, okay, so as I mentioned, right, 1 sign bit and 7 fractional bits are there. Let us consider for simplicity, I'm telling, okay, you can have the much more complex numbers here to discuss here, but that is out of our scope now. Let us see, take some simple example. Like if you take number 1 as a 0.25 and number 2 as one more 0.25. Now I want to add number 1 and number 2. Okay, this is what is the basic addition what I'm telling here. Okay, you are having the 1.7 format. If you want to convert into this 1.7 format, you have to just multiply with the maximum value which is present in this one. So if you remove 1 from here, 2 to the power of 7, which is nothing but 128. If you multiply 0.25, if you take any of the numbers here, which is ranging from -1 to +0.999. So if you multiply with this number, right, 2 to the power of 7, so it will be falling in this range. So if you see here, 0.25 into 128, it is nothing but the value you are getting as a 32. Okay, if you represent in the hex format, hexadecimal, what I mean here, hex is a hexadecimal. Since I have taken for the simplicity number 1 and number 2 both are same, right? So it will have this value. Now, if you represent in the binary format, okay, so each bit, how do we represent here? We are considering 1 as a sign bit and the rest of the 7 bit are the fractional items. So each bit corresponds to these values. Now, if you see here 0.25, this is the way what we represent. And even the another 0.25. What will happen when you add these numbers? You will get this one. Okay, so the value is 0.5. If you see here, means like the processor will take care of this kind of a stuff. Now, what will happen if you add? This is simple actually. So it will be maximum of 0.5. You will get it over here. So this is the way of representation. So similarly, if you go a bit more complex here, right? What will happen is like sometimes there can be a overflow. When overflow happens, overflow means what? It goes beyond the maximum value. Means like you can represent up to maximum of 0.9999 value itself. But if it is going more than that one, so if you keep on adding 0.25, what will happen? Overflow will happen at certain point of time. So when the overflow happens, what we will do is in the fixed point arithmetic, most of the time we will saturate to the maximum value. Means like we will limit our maximum value to 0.9999. If it is going beyond that, we will limit it there itself. Because of that, what will happen is like, because you are saturating abruptly, what will happen is like it will have some signal processing artifacts. So those artifacts may be in the form of distortions or some kind of a things which will come out of this one. So when you see the output, you may see it sometimes as a glitchy kind of thing. So as a signal processing engineer, you should be careful enough to take this, whether I can use my only 8 bits here for addition purpose. For example, multiply and accumulate, I said, right? Accumulate is nothing but addition of the addition of the items, addition of the values continuously. So if I take a 16-bit register, but my values are in the 8 bits, but if I take a 16-bit registers, what will happen? You will have more headroom for this kind of a overflow operations. So you will avoid that overflow kind of things over there. So as an engineer, you should be in a position to judge what should I take. If my input values are 8 bits, but if I want to do intermediate calculations, what should be my register length? So I should be wise enough to choose those things. So you should consider as a signal processing engineer how the overflow is happening. So when the overflow happens, I'll be saturating. So if I saturate, how my algorithm behaves, all those things you need to consider. So this is one example for the simple addition. Actually, you can have the much more complex things over here. So let us limit our discussion till here itself. Now coming to the subtraction, it is a similar way, like the way like how we discussed in the addition, right? Here also the same thing. Let us consider, but here I have chosen a different number because if I take 0.25 and 0.25, it will become a 0. Now let us consider a 0.50 here, and the number 2 is a 0.25. So in straightforward, if you put a pen and paper, you can say 0.25. But if you see here in the binary format, okay, the binary format, when you represent 0.25, you will have this value. Sorry, here's something, the mistake which I have written here. It is a 0.5. 0.5 is nothing but one value extra here. Okay, this is a 0.5. 0.5, which is relates to here. Okay, in the binary format, rest of the things will be 0. So here 10 needs to be added extra. Okay, it's a 0.25. Okay. So basically, right, this is a small typo mistake. Sorry for that. Yeah. Now this looks like this basically. So if you choose the 0.5, this will be the 0.5 value, and this is the 0.25. So if you subtract, what will happen? Your 1 will be carried over here. Okay, and then the 10 will be there here. So when you carry in the binary subtractions, when you carry here, it will be 10 will be there. 10 minus 1, nothing but 2 minus 1, which is nothing but 1. So this will be the value in the subtraction. For example, if the other way around, if it is like num1 is 0.25 and this is 0.5, what will happen? You will get a minus 0.25. Minus 0.25 will be there. So minus 0.25 means how do we represent? Basically, it is a sign extension of this one will be there. Okay, sign extension in the sense like it represents a negative number. It is a 2's complement method of representing a negative value. So this way of means like it is a kind of the same as a addition, but a sign bit will be there here for the subtraction. So you'll be taking care for the sign bit. Now coming to the multiplication. So basically, right, in addition, what will happen is, right, when you add to 1.7, means like two 8-bit numbers, you will get maximum of 9 bits. Means like a overflow will be there. That is why we are considering as a 9 bits. But when you multiply, what will happen is, if you multiply 8-bit by 8-bit, what will happen? You will get at most 16 bits, because n this is many number of bits. When you multiply, maximum it requires a 16-bit of values. So let us take the same example, 0.25 into 0.25. So when you convert into hexadecimal format, it will be like a point. It's like if you take the previous slide, the same values here I'm considering. Okay. So if you represent in the hexadecimal format of the 0.25, it will be 0 cross 20. Same thing. If you multiply with this one, you will get this value in the hexadecimal value. So here what is happening is, if you see the fixed point representation, m.n format, it is a quantization format. Here what we are representing in the form of 1.7 format. Here also 1.7 format. In the multiplication, we should make sure that both the Q formats should be same. Okay. In the addition, so I'm sorry. In the addition, you should make sure that both the Q formats should be same. Otherwise, you cannot add the numbers. But in multiplication, you can choose different Q formats. But you should be very much careful in manipulating these bits. So when you, for our simplicity of our discussion, what we'll take is 1.7 format and 1.7 format. What will happen is, you will get 2 signed bits here, which may not be, which is not required for the representing a number. You require only 1 signed bit. So here you are getting 1 extra signed bit, right? So what we will do here is, basically, we will remove this signed bit and we will allocate the same bit for the fractional portion. So you will be doing 1 left shift. So that left shift, whatever you get 2 maximum 2 sign bits in the MSB, right, will be shifting out one of the MSB signed bit, so that you will have the proper value here. So if you see here, what we are doing based on this operation, okay, once we get this multiplication, you are left shifting this one, okay, 0 cross 800. So as I mentioned, right, it is in the 1.15 format. Okay, if you convert this 0 cross 800, which in turns out to be 2048 value, and it is in the form of 1.15 format, because this is a 8-bit, this is a 8-bit, total will be 16 bits. It is in the 2.14 format. What I'm doing, I'm left shifting by 1 so that it will come as a 1.15 format. So if you want to convert this fixed point number into the decimal number, as I mentioned, right, you need to divide by the maximum value of that one. So if you do this one, what will happen? You will get 0.0625. So the value is same here. So, but when you are visualizing, you have to do this one. But when actual implementations, everything will be done in the integer portion. This is only for visualization part I kept over here. Okay. Now, if you represent here in the 1.15, but let us consider that I don't have a register length of 16 bits. I am using 2 different registers of 8 bits, and then I am representing these values. So at that time, what you need to fall down to? You have to fall down to once again 8-bit. So you need to convert this one to 8-bit format. So here what we are doing, we are converting 1.15 format into 1.7 format by right shifting the bits. With this right shift, what will happen? You will be losing the fractional portion. Some of the fractional portion here, right? That will be gone. So which is equal to 1. If you convert this one, right? If you right shift by 8, you'll get this value, which is nothing but the same 0.625 value. So this is a basic multiplication, what we say. Okay, you can have little more complex items over there here. Okay, but this is only for the visualization part. So if you start working on the same thing, right? So automatically the compiler will take care of this kind of a data type handling. So far what we discussed on the fixed point operations like addition, subtraction, and multiplication. These are the 3 major operations wherever you go in the signal processing. Okay, whatever signal processing algorithm you take, only these numbers only will be involved. Okay, I'm sorry here. Okay, this is not required. So division can be a repeated subtraction, which you can be used. Okay, this is a redundant slide which is being added. I'm sorry for that. Okay, now if you take the DSP, any signal processing routines, right? Or if you talk about the terminologies, like most of the time you will be having the filters. So filters can be either finite impulse response filter or infinite impulse response filter. So in the finite impulse response filter, what will happen? Like you will have the only taps, single taps will be there. There won't be any feedback. That is what the finite impulse response. So when you give an impulse as an input, you'll get finite number of impulses as the output with a weighted related stuff. That is a different case. Okay, but whereas in the IIR, it is a repeated additions and multiplications will be there. Okay, so they are usually, these are the filters what we call. Whatever you take any signal processing, either it may be FIR or IR filter. Of course, when you are designing the FIR and IR filters, you may be using a different complex terminologies, but finally it files down to these 2 kind of filters. Now, if you take any operations, like if you want to compute the output of any filter or any system, there is nothing but a convolution. If you want to compare the 2 signals, you'll be using the correlation. So if you want to convert from time domain to frequency domain, that is a spectrum, you'll be using the FFT. So these are the generic things, but these are the highly computationally intensive. So if you take any noise suppressor or speech modeling technique, right, you require these kind of operations in a left and right in a different fashion. So it involves huge amount of operations. So if you take here, right, if you take the FFT, simple FFT, I'm telling, okay, if you take 1024 radix, means like if you use these many number of bins. So if I'm dividing my complete time domain samples into 1024 frequency samples, you require these many number of operations. See, I'm telling just about 1024. Okay, if you increase this 1024 to 2048, this will be doubled. Means like it is in the logarithmically, it will increase. So if you want to handle, so you will be calling these FFTs in a huge number of times in a second. So you cannot handle the 1 second data as it is. What you will be doing in the speech processing is like you will be converting into the chunks. Okay, when I'm talking, okay, the data whatever you people are receiving, it is not transferred per second basis. It will be transferred in the base of the milliseconds. So usually, right, in any of the speech processing, we will take a buffer length of 10 milliseconds or 8 milliseconds or 20 milliseconds, like that. You will not be considering as the 1 second. So if you consider as a 10 millisecond, you will have 110 millisecond chunks in that 1 second. So you'll be operating only on the 10 seconds. So with the 10 seconds, 10 milliseconds, you will be operating 100 times in 1 second. So you will be calling this FFT those many number of times in the 1 second. So you can imagine how many number of operations are involved. I'm just talking about the FFT. Okay, there will be much more complex algorithms which we will design using these kind of computational things. So this requires a specialized hardware. You cannot do using the regular general purpose processors. That is what the DSP architecture is meant for. Okay, that is the beauty or importance of the digital signal processor in our day-to-day lives, and even in the car infotainment, in vehicular communications, wherever you go. So these are very much critical nowadays. Now, if you see here, right, so in general, as I mentioned, right, this is an IR filter where you will have the feedback from the output to the input. So you can realize this one. And if you want, if this is a generic equation for the FIR filter, means like it is a delayed input of the input with the weights, you can realize the output. So these are the two different methodologies in order to realize any filter you take. Okay, only these weights and the amount of iterations will be changed. But apart from that, everything boils down to only these two kind of filters. Now, coming to this one, right? If you want to realize a output response using a FIR filter, okay, and an IR filter, which is better in this one. Okay. Now, if you take FIR filter, it requires huge amount of delayed information, delayed inputs. So if you want to realize one output, you should have the more amount of history in order to compute the next sample. What is the next sample present in this one? So it requires huge amount of memory and it requires huge amount of history basically. But here, if you see, you don't require that much amount of history. You require very less. You can realize with the second order or third order filter itself. Here you may require something like 128 order or 256 order in order to realize the same thing in the IR filter. Okay, so now, but which is better in this one? Is it when it comes to the computational rate, FIR filter is a bit more complex compared to the IR filter. But when it comes to the power consumption and the cycles rate, IR filter is much more simpler as it requires less number of history and less number of computations. But the disadvantage of the IR filter is like you may not be able to have the linear phase filters. Linear phase means like you will not have the equal amount of shifts for different frequency components. Sometimes that kind of linear phase will not be possible to achieve in the IR filter. But for some of the operations, like if you take the speech processing, right, you don't require that kind of a linear phase always. So you can ignore for some time for that linear phase. So what will happen? You can use the same IR filter where you'll have the less amount of computational complexity and less amount of memory required to store these kind of samples, because history is very less here. Second order means you require only two previous samples. But here it is not like that. You have to store those many number of samples here in order to achieve the same thing. So we have to decide which is better, which is not better. So if you take image processing, you may require a linear phase. So if there is some phase issue there, you may see some artifacts in the image. But whereas in the speech, right, those kind of an artifacts, you can ignore it. Means like your ear may not be able to differentiate between those kind of issues there. So it depends on the use case, which filter needs to be used. So as I mentioned, right, so if you want to have the less computational one, you have to go for the IR filter. If you want to have the more computational means like you have to go to the FIR. So we have to choose which is, so you cannot, there is no hard and fast rule which we have to take this IR or FIR. Depending on the use case, depending on the response what you want, you can choose that one. Okay, and coming to the response time, right? So the response time, which is more responsive, IR filter or FIR filter, which is more converging, because that the response time is more required for us. So if you take the IR filter rate, you can easily with a short number of filter tabs here, means like previous history, very less number of previous history, you can get the more response here compared to the FIR filter. So FIR filter will have the more delayed latency will be there compared to the IR, because you require more amount of history over there. It's not the way like for the IR filter, but it has its own advantages and disadvantages. So as I mentioned, right, so most of the times what will happen is like you'll be boiled down to adding and multiplication. Okay, so you should have a specialized hardware for the adders, multipliers, a parallel stuff should be there. Okay, so at a time I should be able to add the 4 different values in one cycle. So such kind of specialized hardware should be required for adders, multipliers, okay, dividers. So when you want to divide a value, right, you cannot keep on doing the same repetitive subtraction method. Okay, because that consumes a huge amount of cycles. So what they have done is like they have used the Newton-Raphson method, and then they have created specialized hardware for the dividers and the shifters. So when you want to shift the value, you should not take the more amount of cycles. You should have some specialized hardware for the shifting. So it should consume only one cycle to shift. Otherwise, if you want to shift one by one, it takes its one time. So these shifters, dividers, multipliers. So we will be calling some huge million operations, millions of times we will be calling for small 10 milliseconds of data. So you should require a specialized hardware for these things. Another one is a circular buffer. So for example, if you want to use the FIR filter, so this is a filter coefficient. So you should store somewhere else. So you keep on rotating your pointer from starting to ending. It is a cycle consuming process because you'll be calling million amount of times. So at that time, what we'll do is this circular buffer, what it will do is like circular buffer means, you know, right? So it will have the 2 pointers. One is the starting pointer, another one is the moving pointer. So once this moving pointer reaches to the end, once again it points to the starting pointer. So what will happen with this one? No need to have any separate hardware to find out means like where my pointer is, whether I need to shift anything over there, not required. So it automatically maintains this one. So it is a specialized circular buffer, what we say. Okay. And then parallelism, as I mentioned, right? Parallelism is very much required in your ALU operations, arithmetic logic unit. So if you want to do the multiplications, 4 multiplications in one shot, 4 additions in one shot, so you should have the parallelism in the ALUs. So you require this kind of a specialized hardware as part of the DSPs. Now, as I was telling right previously, like there is something called pipeline and parallelism. Most of the time we will get confused actually. What is the difference between pipeline and parallelism? Parallelism means you will have a separate hardware for different functionalities. For example, I am having 4 parallel adders. What it will do? 4 additions can be done in a single cycle, but each operation can be further split into multiple sub operations. Like for example, if you want to add 2 values, what will happen? First of all, if you have some computer background or if you have some microcontroller background, right? What will happen? You have to fetch the instruction from the memory. You have to fetch the data from the memory. You have to do that operation and you have to issue or execute the thing. This is what in general any of the microprocessor architecture will be there. So these fetching of the data, fetching of the instruction from the memory, that is one subtask which you can consider. Okay. Fetching of the data, that is one instruction, one small subtask you can consider. And then decoding of that instruction or data, that you can consider as one more small operation. Okay. And then finally executing the things, that is one more sub operation you can consider. So these sub operations you can do in a single cycle with a multiple operations. So for example, I have 3 instructions. So first instruction will be fetched. So when the second instruction is fetched here, the second operation like decoding of the thing can be done in the here itself. So it will be like this. So you'll get in a single cycle multiple operations, means multiple parallel things. Okay, this is a compiler based and the processor based. So you can have the pipelining of 13 stages or 18 stages depending on the processor. So if you take the Cortex processor, right? For example, I'm telling Cortex A8, it is like basically 13 stage pipeline, means like 13 operations can be done in a single cycle. So that what will happen? You will, without having a parallel hardware, you will be able to achieve that parallelism in this pipelining itself. So this is the basic difference between the pipelining and parallelism. So parallelism requires extra hardware, whereas pipelining requires no extra hardware. It is a software based one. Okay. So basically, if you see right how the memory is means like how the memory is defined or memory is organized in any of the DSPs, right? There is something called von Neumann architecture and forward architecture. So in von Neumann architecture, what will happen is like you will have the same memory chunk which is allocated for the data and code. It's like you can use the same memory location for the data and code. Whereas in the hardware Harvard architecture, you will have a separate memory blocks for code. Code means instructions. Data means the actual data. Okay. So for example, if you want to add, okay, 2 plus 3. So add is an instruction which can be stored here. 2 and 3 can be stored in the data. So when you have this one, what is happening is you will be using the single bus to get the data, and you will be having the same bus for the code as well. Okay, so when you do this one, what will happen is like means like you have to wait first. Here you need to get the instruction, and then you need to get the data, and you need to wait. All those things will be there. Here you can get the parallelly both instruction as well as the data. So this is advanced compared to the Van Neumann architecture. Advanced in the sense, what I mean here, it means that it is more faster compared to the Van Neumann architecture. So this is the way like we can differentiate based on the memory architectures of the DSP processors. So if you want to have the faster memories, so you can go for the caches, cache mechanism. You might have heard about the caches, right? So caches are the very fast memory units, which are very closely coupled with the processor, central processing unit. So with this one, what will happen? So regularly, whatever you are getting the data to the processor, right? You can put it in the cache. You don't require to fetch always from the external memory to the processor. You can use the caches, and then you can read and write from the cache. So it will be very fast if you use the caches. So if the cache size is increased any of the DSP processor, what will happen? It will be more cost compared to the one like without caches. For example, you might be seeing latest Intel processors, right? That will be told in terms of MBs, 80 MB, 8 MB of cache, okay, 10 MB of cache, 12 MB of cache. What does that mean? So that much amount of memory is very closely coupled with the processor, where you are storing the data or instructions which you are more frequently you are using. So it will have that data in the cache itself. So whenever there is a requirement of the data, it will fetch only from the cache. It will not go for the external memory. So with that one, what will happen? Your fastness will increase. Okay. Because if you want to read from the external memory, it will take more number of cycles, because your processor is operating at a certain speed and your memory may not be operating at the same speed. So it requires some kind of a delay here. But if you have the caches, that kind of an issue can be removed. But there is one more disadvantage. For example, if you want to flush the cache, what will happen? So you need to flush the cache and you need to get the fresh amount of data to that one. Okay. There are various methodologies, various techniques how the cache is managed, cache is operated. Okay. Depending on the processor architecture, depending on the processor complexity, those things can be managed. Okay. So as this one, cost, power, and efficiency, these are related to this one cache. Okay. How they are based on this one, how they are closely coupled to this one. Okay, these all things will be handled by a memory management unit. So there will be a separate arithmetic logic unit and then memory management unit. So fetching of the data, reading of the data, writing to the data, reading from the IO devices, all things will be maintained by the memory management unit. Arithmetic logic unit, the main functionality is just whatever the data is coming from these memories, right? It will do the operations and it will give out. So you will have the separate arithmetic logic unit, memory management unit. Okay. So if you have these kind of things, right, your architecture will be so fast, your hardware will be so fast. So that is the beauty in the DSP architectures. Okay. If you take the general purpose processor, right, you may not have the specialized hardware, was what I was mentioning about this one, right? Adders, multiple, these things, there won't be any specialized hardware in that one. So if you want to do a division, it will be doing a successive subtraction method. So what will happen? It will take its own time, but here it is not like that. Okay. So those things will be the separate hardware modules which are present in the DSP processor. Okay. Another one more thing is the RISC and CISC processors. Like so far what we have discussed based on the type of operations like floating or fixed. That is one way of differentiating. Another one way is the Van Neumann architecture or Harvard architecture based on how the memory is managed. Now coming to the instruction set. So instruction set you can develop actually as a developer. One person can write his own customized instructions, or he can also use whatever the instructions present as part of the regular typical hardware. Okay. So RISC means what? It will have the very less number of instructions, reduced instruction set computer. What does that mean? It will have the less number of instructions. With these number of instructions, you should be able to process your algorithm. Okay, that is what the reduced instruction set. So it will consume more cycles because you will have only limited number of instructions and you need to achieve the certain thing using this instruction set. So you may need to write more number of operations for that one. So that is what is the RISC. CISC means what? Is a complex instruction set. So complex instruction set means like it will have the very more complex instructions. Like it can do multiple things in one shot, that instruction. That is what the complex instruction. So parallelism will be there in that one. So here you will have what complex instruction set, and you can achieve this one with a lesser amount of cycles. But what is the difference between these two things? It will have the extra hardware compared to the RISC. That is what we call it as a VLIW, very long instruction word. Very long instruction word means like it will take the huge amount of length of your register. So it requires some specialized hardware. These are more costlier compared to the RISC, but these are very fast. There is one more thing called SIMD, single instruction multiple data. So what does this do? Only one instruction will be there, but it will do the multiple data operations. For example, I have an array of 100 values. I want to add all of them, and I want to put it in a single register. Like I have 100 values. Let us consider an array of A, which is ranging from 0 to 99. I am doing a normal for loop. Okay, in that one, what will happen? You will be having a sequence thing. In the SIMD, what will happen is like one data means like one fetch. It can get the 4 values at a time. With a single instruction, what it will be doing? It will add the 4 values at a shot, and then it will put it in a register. That is what is the SIMD. So single instruction and multiple data. That is what is the SIMD. So these are some basic features of the CISC, what I'm trying to say here. Superscalar. Superscalar means that the Harvard architecture is there. No, that is what we call it, a superscalar, and it will have the much more complex hardware, because it will have multiple instruction memories, multiple data memories, multiple instruction buses, multiple data buses, where you can handle the multiple things in a single cycle. That is what is a superscalar. What do you mean? Okay, so these are the major DSP categories or DSP differentiations which we can do. Now, so far what we have discussed is like initially we discussed with the signal processing routines or functionalities which are present in the in-vehicles or in a car infotainment related stuff, and then later how they are translated into the actual in-car communications related stuff, and what are the various signal processing techniques. Later, how we have achieved using the hardware, that's a digital signal processor. We have given the explanation, and then from there we have discussed all the instruction, all the different architectures, the implementations, and the fixed point we discussed so far. Now we'll take one case study. So the case study is like this. Okay, we'll start with the ARM processor. So there will be many number of processors from Qualcomm and all that one will be there. So we will limit our discussion to the ARM processors, because ARM is like the more ubiquitous nowadays. If you take any of the mobile phone, or if you take any of the car infotainment system, ARM processor is by default, it will be there as part of that one. So we'll take some small case study on the ARM processor. If you see here, okay, its evolution has started from 1995. Now, okay, I have only data for the 2015. So later point of time I was not having, but almost it will be the same kind of an architecture what we have here. Okay. Now, if you take initial version, it is having only the thumb instructions. Thumb instructions, it will be operating only on the 16-bit data. Later, it came with the ARM instruction where it will be operating on the 32-bit. Okay, what we consider as a architectures of ARM v4, version 4 architecture, version 5 architecture, version 6, version 7, version 8. Now version 9 is also running. Now if you see here, what is being introduced in each of the things, here there is no floating point unit. It's completely a fixed point processor. In ARM 17 v4 architecture, there is no floating point here. In ARM v5, what they have introduced, they have introduced a vector floating point unit. It's like you will have the floating point operations present in the ARM v5 architecture. In the v6, what they have done, along with the VFP, they have added the SIMD as well. SIMD in the sense like basically, as I mentioned, right, single instruction, multiple data. So where in the ARM 7, right, what they have introduced something called a Neon. So Neon is nothing but a specialized unit where you can load 8 16-bit values at a time. That is what is the Neon engine will do. It is an advanced SIMD, what we call advanced single instruction multiple data. Okay, and then this up to here is all based on the 32-bit. Now in ARM v8 and ARM v9, what they have done is they have introduced the 32-bit and 64-bit architectures. So previously only up to, if you take Cortex A8, A9, okay, they are like more on the 32-bit architectures. Now if you take the ARM v8 architecture or v9 architecture, where you have the 64-bit architecture as well. So if you see here, right, but there should be some compatibility issues may come into picture. So they have done a 2 different kind of a flavors. So where you can operate the same processor in the 32-bit format or in the 64-bit format. So when it is operating on the 64-bit format, right? So you will not be able to do 32-bit operations. It's like a mutually exclusive kind of thing. So this is a small, what you say, case kind of thing, how the ARM is evolved. So if you take the let us take small example on the ARM v7A architecture, which is little easy, or means like we can take ARM v8 as well. Okay, where I'll be explaining what will be the in detail inside the present in this one. So if you see here, right, ARM v7A and ARM v8A. In ARM v7A, there is separate hardware floating point unit. So where floating point unit is in the hardware, where you can do the floating point operations in the hardware itself. Means like you don't require any separate software to do that one. So if it is a hardware floating point unit, what will happen is like your memory, your power consumption will come down. Means like you can do the operations in a very fast manner compared to the software one. As I mentioned, right, it will be having the Neon engine. Neon engine is nothing but an advanced SIMD where you can get the multiple amount of data in one single shot. Okay, all these things will be present as part of the ARM v8 architecture or ARM v9A architecture as well. But okay, there is something called 64-bit format in the ARM v8, which is not present in the ARM v7A. There is something called trust zone. Trust zone is nothing but when you are operating, security is more important. Somebody should not just access your processor and you can, means like the basically, right, viruses, or if you take any vehicular communication, some security is required for your data and for processing whatever is happening in your car or in your vehicle. So for that one, you require a trust zone. This trust zone is nothing but a specialized hardware or specialized module which is present on this advanced risk mission ARM processor. Okay, where it will what you say encapsulate, it will secure your data and instruction, whatever processing is going on. And it's like, yeah, if someone has to enter from the outside world to this one, it has to go through this trust zone methodology. It's like in your coding itself, you should be having your own security features. So and then virtualization, so you can connect multiple things and you can make it as a virtual environment. Virtual environment in the sense like I'll be having multiple amount of IO devices connected, but how I will be handling with that one, some virtual addresses I will be giving, not the physical addresses. So there will be kind of virtual to physical translation units will be, that is what nothing but the virtualization extension. And then it will have the large physical memory address extension. Usually, right, if you take the older memory formats, if you take this ARM v7 itself, it is a 32-bit, means like maximum address location what you can do is 2 to the power of 31 you can be able to, but it will have the capability to take the more than 32-bit. Okay, it can go for 64-bit or 128-bit kind of thing. So it will have that kind of an extension. Because of this virtualization, you can do these kind of an extensions. Okay, same thing here, right? A trust zone, they have done a crypto here. So basically this crypto and trust zone, they are kind of a similar things. Okay, so they have added extra things over here. Okay, more amount of caches can be added, more amount of IO devices can be added. Okay, those are the major differences between these two things. Yeah, as I was mentioning, right, previously, like the evaluation ARM v4 architecture. Okay, and then comes to the ARM v5, ARM v6, and then ARM v7. Okay, these are the basically, so this is the capability. Capability means nothing but the processing power. This is the performance, and the means like performance and the functionality, how they have been increased. Okay, now if you see here, they are like less capable kind of thing. Now if you take the ARM v7A architecture, nothing but Cortex A15, A9, A8, A7, there are many things. Okay, we can consider as the ARM v7A architecture, which is the very high advanced in the computational complexity or usage point of view. Okay. Okay, these are some of the major DSP players what we can consider. Okay, if you take the Qualcomm, they have their own DSPs, which we called as a Qualcomm DSPs, like Snapdragon and all those things. Okay, they do their own custom processors and all that one. Okay, and also they will be having the ARM processors as well as part of the Qualcomm portfolio. Okay, and even NXP Tensilica, TI, Samsung, Apple, they have their own processors, or they have their own DSPs. Okay, but they will be abiding only to these rules and regulations. So nothing different. If you take the fixed point processor, means all the operations will be like this. So if you are clear enough on the fixed point operations and floating point operations, right, you can move to any DSP processor just like seamlessly. So each processor will have different capabilities and functionalities and all that one. So depending on our case-to-case basis, we can choose the one which is good and which is bad kind of thing. Now, if you see here, I'm not sure, I'm running out of time. It's 11 o'clock is almost. Can I take 15 minutes extra, or how this can be done, madam?
Yes, sir, you can proceed, sir.
We can consider, because so that all the things I can cover in this one. Okay. Now, you see, right, if you come to the any industries, like any major DSP players, like as I was mentioning, right, Qualcomm, NXP, Tensilica, they have their own signal processing team will be there. So how usually, like, what is the flow there? How they will start algorithm development, how they realize on the processors, because starting from the scratch to the end product, it will have its own phases. How this will be done, I'll give a small glimpse. After that, we can end our session. Okay. Now, if you see here, any algorithm study, right, what will happen is, like, first of all, it comes with a use case. For example, I want to do some this operation. So how to do this one? There may be many methodologies. Okay, go to the IEEE website, get the corresponding papers, read the papers. Okay, finalize. Oh, this is the way we can do it, and you can start building your prototype either in MATLAB or Python kind of thing. So, for example, I want to do a noise cancellation. So noise cancellation can be in time domain and frequency domain, or frequency domain. So which one is important? You will be studying, okay, this is what is the performance. If I do in the time domain, if I do in the frequency domain, I will get this kind of an advantages. But what are the complications in the CPU computations? We need to understand. So based on that one, okay, this maybe like a time domain may be best suitable for my use case. That's what I realize. Now I'll take that certain portion and I will start implementing in the MATLAB. Maybe with the existing, because FFTs, FIRs, IRs, those things will be easily available in most of the signal processing routines. So you'll take those things and you'll start building the complete use case. So input digital data will be given to that one, the module, and the noise suppressor. Okay, noise suppressor is one big black box. Inside that one, you can have the sub modules, and then it will do all the processing. It will get the output. So for different types of noise characteristics, how my system is behaving, how my prototype is behaving. So once I'm satisfied with my prototype, I'll end my prototype or evaluation of my use case over there. I'll stop there. Okay, I have now MATLAB code now, which is implemented in that one. And then I'll take that MATLAB code as a base version and I start writing a C corresponding code, because you cannot write MATLAB code or Python code on the signal processor. At the end of the day, everyone has to boil down to either C or C++ if you want to run it on the signal processor or in any general purpose processor. Now, if you take, okay, I have the complete MATLAB code, I'll be writing a equivalent floating point C code, because directly you can also write the fixed point implementation, but it is a little complex what we consider in the industry. So you will have one reference floating point code where you take the FFT module in the MATLAB. Okay, you will see what are the operations and you'll write equivalent C coding for that one. Okay, once you have the floating point C code which is running for the use case, you will evaluate once again in the MATLAB to see how the values are coming over here. Okay, and then if they are matching, yes, my reference implementation on the floating point is now done. Okay, it is perfectly fine. Now, if I want to use on the floating point processor, directly go and dump into the floating point processor and you can start using that one. Okay, but if I don't have the floating point processor, what I'll do, I'll convert this floating point operations into the fixed point implementations, and then I'll realize them on fixed point flow of the data. So now I have the MATLAB code, floating point code, fixed point code. So if you see some issues in the fixed point, what will happen when you are limiting your data length to only a certain number of bits? What will happen? Definitely you'll be able to see some kind of an artifacts, some kind of a distortions, whether these distortions are acceptable. If they are not acceptable, what I should do? I should do some kind of an processing or different methodology in my fixed point implementation. So that way, back and forth, and then kind of a closed loop evaluation, all those things we'll see it, and then finally I have a C implemented either floating point or fixed point. What I'll take that module, and I will integrate into the framework. So this is an individual product. What you say, sub-module, what we can say. Noise suppression is a sub-module. Speech codec is a sub-module. Speaker recognition is sub-module. It cannot operate directly when you put it on the processor. You have to have some kind of a flowing mechanism. Okay, so that you will go and integrate to the existing framework. Okay, now the data will be coming from the mic. So that is converted into A to D converter and given to your noise suppressor. And the noise suppressor will do these things, and then it will remove the noise and it will give out the clean speech. That clean speech will be given to the D to A converter and given to the speakers kind of thing. So this is the general flow. So you will go and hook your module into that one, and you will see how your system is performing, whether any crashes are there, any issues are there. Once this is done, okay, you'll go to the customer, or you will directly deploy in your products. This is called the mass production, what we say. Yeah, this is what is the thing, what is happening on my mobile phone or in car, whatever is the thing. So this is the generic algorithmic development, what will happen in an industry, usually. Now, if I take a small example, right, I'll not take more time. I'll take maximum of 5 to 10 minutes to finish up this one. Okay. So if you take here, right, I have taken one of my favorite algorithm, which I have implemented very long back. So it was one of my favorites one. So just I have taken for an example here. Because of the IP related stuff, I'm not going to give in detailed explanation, but I will be taking a flow of the data and what is happening over there. Now, if you take here, right, this is a kind of a basically, right, audio slow motion. So audio slow motion is nothing but what is that one? Basically, you will be having the audio and you are slowing down the signal. For example, if you take the latest mobile phones or thing, right, what is happening is, right, you can play the content in the slow motion. What do you mean by slow motion? Like when you are having some kind of a video data, you are slowing down the data to see how it is happening. But the corresponding audio, you don't have the corresponding audio. So if you take any of the most of the advanced applications, you'll be having most of the time video related stuff, but you don't have the audio related stretching of this one. That is what nothing but the audio slow motion. You'll be playing the same audio in a very slow fashion format. Usually, right, what is the application of this one is like if you are hearing something like non-understandable language, like if you are going to learn something like French or German, so you want to hear very slowly, you don't want to be very fast. So what you will do, you'll slow it down. Okay, sometimes it is okay that I can go a little bit faster and then I can play it. So if you see, take the YouTube and related stuff, right, you can play 1.5 times or 2 times kind of thing. But if you go beyond that one, your voice quality, whatever is being created over here, it will be more of metallic sound. It will not be more intelligible. Okay, so such kind of things we have to use the phase vocoder, which is a very complex algorithm basically in the way. So, but that can be used for the very high stretch amount of data, like 4 times, 5 times of your speed. Okay. Now, if you see here, the basic building blocks of this one of the algorithm is like you will be having the, yeah, for this one, I have referred one of the IEEE paper. And from that one, I have derived the actual things, what is present as part of the phase vocoder. It was done very long back, actually, by the way. And then in between, I have tweaked some of the things to make it more optimal or more efficient. So if you see here, right, so I took that IEEE paper and started to write. So if you, this is a black box, big black box. So in this black box, I have divided into 3 modules. This is a short-term Fourier transform, linear interpolation, or extracting the samples, and then you are converting back to the time domain. So this is short-term Fourier transform. What does this mean? Is like you'll be having the windowing and then FFT. Why you do windowing? In order to remove the artifacts. Because if you want to have the smoother, you are not operating on a second basis or a complete chunk of data. You are operating on the real time. So in the real time data, you will take chunks of frames like 10 milliseconds or 20 milliseconds. On that one, you'll operate. So when you come in all those 20 milliseconds, just like that, you'll see the artifacts. That is called the Gibbs phenomenon, what we say in the signal processing terminology. So what we'll do, first we'll do the windowing to smoothen the data from one window to the other window. And then after doing that windowing, we will apply the FFT. That is called nothing but a short-term Fourier transform. So the window I have used is the Hanning window. You can use the multiple other windows, but this is very simpler to implement actually. Okay, then more efficient as well. So once you get here the output of this one will be in terms of samples in the frequency components. In the frequency domain, what I will be doing is I will be estimating the missing samples, because when I am doing a stretching, what I will do, I will be adding extra samples. So if you want to add the extra samples, you need to find out. There is nothing but using the linear prediction and the phase corrections. What we see, we will create a new samples. So once you have all the samples here, what you will be doing, you will reconvert it back to the time domain and give the output signal. So this is the basic thing. Means like this is the way which a person or which a engineer in the industry will follow this way actually. So this completes the complete basically, right, we have discussed what are the various signal processing techniques, and then what are the various things which are present in the car communications related stuff. From there, we went to a little deeper into the signal processors. We discussed very in detail about the operations and then different types of architectures and all that one. And from there, we have taken a case study of the ARM architecture, and then we have seen how it has evolved. And finally, I have given some kind of an example how we work in the industry. With this, I am done with my session. And if you have any questions, you can.
Okay, sir, there are two questions, sir.
Yeah.
The first question is, nowadays, which generation of ARM processor is used in fully autonomous vehicle? And how should we start our journey with ARM processor? That is the roadmap to know the functionality of ARM processors.
Okay. So if you see, right, there are a lot of white papers which are present in the ARM website. So if you open that ARM website, and then if you go through the what are the various, because I'm thinking in a perspective of a new person who wants to work on the ARM processor. Okay, so he has to understand the how the journey has happened. Okay, there are many white papers which are present as in the ARM website. You can take one of the white papers. So by seeing that one, you will be able to understand which paper needs to be chosen for that one, because the titles will be very straightforward, like how the ARM architectures has evolved, and then what are the different functionalities in each architecture. It may take a couple of days to understand that which processor is what kind of thing. Usually, like Cortex X processors, which are used. There is something called Cortex X processors are majorly they are used in the car infotainment systems, and they can go to that Cortex X processors. So once they see the different architectures, right, they will be able to understand for the use case what processor is useful for them. So when it comes to the tools point of view, right, for the industry, right, it is a licensed version. But as far as my knowledge is concerned, for the institutions, through the institution, if you require, you can raise a request to the ARM people. In the contact list, there will be some people will be there, and you can you can raise a request through the institution, and you will get the license to that particular institution. So if you want to run those tools, right, so first of all, you should be very well versed with the C coding, because C is very important if you want to write any DSP algorithms. So if you are thorough in these things, right, I think it is a good starting point for anyone to start with.
Thank you, sir. I think the question is clear. The answer is clear to the participant who asked this question. You can just post. There is one more question, sir.
Yeah.
What are the important issues to be considered in designing and implementing a DSP system?
Yeah. So basically, right, once you choose the bit format, okay, this is my bit format, either 16-bit or 32-bit kind of thing, right? So you can go with any of the processor, like 16-bit processor, maybe from Qualcomm QDSP or from Tensilica, anything can be possible. But you need to find out what is the capability of that processor. So how many IO devices you can connect to that processor. For example, I want to work on some sensor data. So I have to connect the sensor to that processor. So how can I connect, whether that feasibility is present in that processor or not? That is one thing. Okay. So if that is present, let us consider in all the processors. Next thing, what it comes is like power consumption. How much power this processor is taking. So if you finalize, okay, this is what is the efficient processor, where I have the capability of connecting my sensor module to this one. And then now when it comes to the usage point of view, so whether this can be, what are the tools available for that one? For example, I might be having a best algorithm, which is designed in MATLAB and C code, but when it runs on the processors, I will be seeing huge amount of issues. So whether that processor team or corresponding company like Tensilica or QDSP, whether they are able to support my kind of queries. For example, I'm facing some issue which the data, which the content which is present in the online may not be sufficient, or their kind of a documentation is not sufficient. Sometimes it happens because we don't know what kind of issues can comes into picture while running your code. Sometimes we will not be able to assess whether it is an issue in my code or issue in the processor. Sometimes it happens like that. So when you ask such kind of questions to them, whether they are in a position to give the answers in a very short time or not. So those all things comes as part of your decision making of which processor or which kind of a thing I need to choose.
Thank you, sir. And one more question, sir. Like what we have in what we teach students, DSP processor, we have a TMS 320C6714 processor, sir.
Yeah.
And we are actually, if you want to implement, like how you said, real-time noise cancellation, like if you want to make a model to filter out the noise and get a clean speech signal, should we design filter in MATLAB and then import it to the processor?
Directly, you cannot import actually, as I mentioned, right? If you take any DSP process, it will not be able to understand your MATLAB code. Only it will understand the assembly coding.
So the
Assembly.
coefficients should be do what is the procedure? So like we are using Code Composer Studio for
Yes. Code Composer Studio. Code Composer Studio, if you see, right, it is more of C coding actually. It does not have any MATLAB implementation in that one. So now if you have chosen the some noise cancellation technique, okay, there will be many methodologies in order to do that noise cancellation. Okay, minimum mean square estimation, spectral subtraction method. There are many methods are there. Okay, time domain methodologies and frequency domain methodologies. Okay, you first of all, for your use case, for our use case, which is the best algorithm? For example, I want to have this much amount of noise suppression which is present in the room. For example, in my room, I'll be having some noise content and my speech content. So input and output of your signal processor or noise suppressor. So input, I'll be having one SNR, okay, signal to noise ratio. When it comes to the output, it will have some signal to noise ratio output. So whether the signal to noise ratio at the output is sufficient with this algorithm or not. So now you have chosen your algorithm. Okay, this is what I'm getting the signal to noise ratio output. Okay, and then I'm happy with this one. So you will be implementing that one in the MATLAB. So implementing in the MATLAB is not a big task nowadays. The reason is once you have broken down your noise suppressor into different small modules, all those sub modules you can get it from the internet or in the many MATLAB sites you can get it. So you just hook it and then you try to see the complete flow, how the data is flowing. Once you are thorough enough or once you are fair enough to see that, yeah, my prototype is behaving. Okay, I'm giving one speech signal which is added with the noise. Input, I am having this much amount of signal to noise ratio. And when it comes to the output, this much amount of noise got reduced. That is signal to noise ratio at the output. This is fair enough for me. Yes, now it is a time to start writing in the C code. For the C code also, most of the time, you will be getting the standard DSP routines from the TI in the Code Composer Studio. When you install, they will provide some standard software, some like standard routines. And even if you take 67XX processor, right? So it will come with its own hardware capability. So you need to understand the hardware capabilities of that one. So I may be having one FFT, and their FFT module is completely in hardware itself. So you don't require to write any specialized software for that one. You just need to call that routine in the Code Composer Studio. So once it is running on the C67X processor, right, like this, you need to keep on modifying module by module. You have to make the complete module into sub modules so that it will be very easy to start with the, okay. So if it is an FFT, okay, take the input FFT, what it will be there, time domain signal will be there, output will be the frequency domain. So when you write the same thing in the MATLAB, you know what the output will be coming, whether I'm getting the same output or not here. So like that, you need to go on plugging in the sub modules. So once your system is done, everything will be done. So this is the flow what we can consider in the TI environment, or in general in any environment we can consider the same way actually.
Thank you, sir. Which processor will be used in an automatic vehicle, like car engine, car you just showed in the beginning slide? So almost all modules were there. So which processor, is it ARM processor they're using, ARM7 or ARM8, sir?
I'll tell you, if the ARM7 and ARM8, they will ARM7 processors means like they will not be using actually, because they're like they will not be in a position to handle such kind of a very complex tasks. If you see my initial module, right, like basically, right, it will have multiple parallel things needs to be done. So there will be two different processors will be there usually. So what will be happening over there is like there is one thing can be considered as a digital signal processor, another one is a control processor. In the digital signal processor, where it is only meant for running your DSP signal processing algorithm. There is one more processor called control processor, which will be controlling all the other things, control related stuff. So dual core kind of thing will be there, dual core processors. So if you take Snapdragon, okay, usually it is from the Qualcomm. Even in the ARM also, you can go for the Cortex X related stuff, ARM-v80 and ARM-v9 architectures. So where it will have the multi-core, 4 cores, 6 cores, it can be having the multiple times. So you can use two different same cores. That is called the big Indian architecture. Maybe the person who has asked, he can note it down, the term big Indian architecture. So the big Indian architecture, what does that do is like, it will have 2 ARM processors which are combined, closely coupled, where one will be acting as a DSP processor, another one will be acting as a control processor. So when there are no DSP operations, so DSP processor can be shut it down by the control processor will be always awake. So it can do the general control processing operations like engine diagnosing. Those things can be done in the control processor. But when it comes to these speech processing and image processing, video processing, right? That will be transferred to the DSP. So if you ask me the digital signal processor, which are means like embedded in the car, right? There is something called Mali graphic processor, where it can handle the separate graphic related stuff. There is something Cortex related, Cortex A series application processor, where it can handle the speech and audio related stuff. And control processors, you can have the same processor, but with the customizations for that one. So this we can consider as for that one.
Thank you very much, sir. I think it's very good presentation, sir. Starting from DSP functions, you have covered on DSP processor, the data representation, fixed point, floating point, and the DSP architectures, the different processing routines like FIR filters, IR filters. And lastly, you covered even on ARM processor. Very good. I think we got very good insight of all the DSP functions that will be used in the autonomous driving vehicles. Very good presentation, sir. Thank you very much, sir, for your valuable time in spending in this for this FTP program. Thank you, sir. I
am also thankful to the MS Ramaiah for giving this opportunity and for conducting this kind of a FTP sessions.
Yes, sir.
Thank you very much.
It was very interesting, sir. I think
thank you.
I think we can approach you anytime, because we'll be doing some small experiments in the lab, which might not be useful. We'll do only small experiments. We'll not do like this noise cancellation or like application point. We are not doing. So if you have any doubt, I think we will come.
You can always approach. And even one more thing for the audience who are present over here. So basically, right, I work in the audience, as Madam was mentioning in the initial profile discourse. Okay, so as part of this audience, right, we have our own chipset, but we don't do car infotainment side. We do more on the IoT side. IoT edge computing, basically speaker recognition is one of our major strength here. Okay, most of mobile phones, remote controls, in the TV systems, we use our standard algorithms and our own processors. It is a customized processor which we have designed from the Tensilica. So if the institutes or if any of the people, those who are interested, so they can approach me. I have my email ID. You can, Madam, you can share my email ID with the participants. So if you have the very good use case for that one, right, you can approach me over the email, and as a principal engineer, I will be able to take the decisions whether we can do anything for that one. So we will provide our own DSPs, and then with a complete evaluation kit where you can develop your algorithm and you can showcase to us. So it is a kind of a win-win situation. We can do the patenting and all those things kind of a stuff. So it is a kind of a, what we call is study collaborations with the industries, means like industry and then educational institute. We have our own collaboration systems over there. We can do the collaboration, and then we can start working from there. So if the people who are interested, if they have some very good use cases or good kind of a thoughts on this implementation on that, because getting an idea is very important rather than implementing, because getting ideas are very, that means like that is very sophisticated in my view. Implementation is simple in my view, at least. The reason is like having the problem is a big problem for everyone actually. So if you have the problem, we can find out the solutions. So we can do such kind of a collaborations. So to all the participants who are here, so I will be very happy if I see any kind of such kind of use cases. You can approach me, and even in your day-to-day cases, like in your studies, right? So whenever you are doing some kind of adaptive filtering or neural networks or whatever kind of thing, so you can approach for any such kind of doubts on the implementations on these kind of things.
Thank you, sir. There's one more question from the faculty, sir.
Hello, sir. This is Manjunath.
Yeah, hi. Manjunath.
Sir, I have one question. I just wanted to know which algorithm will be used in the VANETs and how it is different than when it compared with your algorithm, sir.
So VANETs is basically like, can you explain a little bit on that one? Because I'm little poor in the car infotainment systems. So what, this VANETs is basically, right, if I understand, there are two vehicles, they will communicate with each other. Is my understanding correct?
Yes, sir. Yes. Sir.
Okay. Now, coming to this one, right? So the communication between two cars, okay? So car one want to communicate to car two, or the vice versa can happen over here, okay? So here, the sensors which are present on the car, the sensors which are present on the car two, they will collect some data and something has to be communicated to the other one. So if you take any of the ARM process, what I was explaining to you there, right? So there is something called crypto mechanism, because the third car should not involve in this car one and car two. They should not come into picture, or they should not hack the data kind of thing. So there, what we will be doing is like, what kind of a communication is important for us there, okay? Because VANETs can have, it's a kind of a ocean, if I understand properly. So what kind of a communication is there between car one to car two? If it want to send some kind of a sensor data, or like telling that, you see, here I'm stuck in the very near to here, you can take a path from the other place. So such kind of communication or anything can happen in this VANETs. So if you take a processor, the processor characteristics I'm telling here, okay? So usually the characteristics should be in such a way that most of the processors if you take, they have the capability of doing these ALU operations. But when it comes to the VANET, security is more important. So some other thing some other person or some other car or some other vehicle should not involve or enter into this domain of the car communication between car one and car two. So such means like the process where such kind of security is given, that is called crypto, or what you say, cryptography kind of thing. So where and then so it will avoid the involvement of the extra person into this one. So for the VANETs, right, such kind of an ARM processors, or even means like, as far as my knowledge is concerned, ARM processors is one of the best processors where you have this kind of a security features. If you take ARM v7 architecture, v8 architecture, v9 architecture, you take any of these three things, right, it will have this trust zone kind of a feature which is present as part of the regular processor. So in that VANET communication, right, you can use this kind of processor where you have the trust zone capability, which is present in ARM v8 and ARM v9 architectures.
Thank you, sir. Thank you so much for your valuable answer.
So there is one more request from the participants, because we have given your email ID. Now, one of the participants is asking, we are interested in collaboration for the topic multi-drone moving target tracking system, which is a proposal funded from Adama Science and Technology University, Ethiopia. So they want you as an external expert in the research work.
Sure, madam. They can drop me an email, and then from there we can start on.
Yeah, I think the participant, whoever has asked the question.
Yeah, please note down my email ID.
We have sent in the chat.
We have posted in the
chat box.
That is great then. So please take that one as there. And then from there we can start on. You can start sharing your request, and then we can have a short sync up meeting after that, whenever you and myself, we both are free, and then we can see from there how we can go on.
Okay, sir. Thank you so much, sir. Thank you for participating in this workshop, sir. Thank you, sir.
Thank you very much. Yeah, with this, I am ending my session. Thank you very much.
Thank you, sir. One second, sir.
So kindly, if you can share your presentation slides so that we can share with our all the participants.
Sure, madam. I will share it right away. Okay, after this meeting, right? After this session, I'll send out that one.
It was a very great session, sir, and very informative.
Yes.
A lot of information has come forward. Let's
yeah,
see.
thanks very much. Okay, thank you very much too. I'm very much blessed to hear such words. Thank you.
Thank you, sir.
Thank you very much, sir.
Thank you. Yeah, bye-bye.
Participants, there is a delay in the second session. I think we will start at 11:50. 11:50.
There was some emergency with the speaker, so he requested for additional half an hour extension in his session. So we'll start around by 11:55. So kindly join by 11:50. Thank you.